Good day and welcome back for the first part of our discussion on differentiating trig functions. Just a quick reminder as to where we are at in the course. We've introduced the concept of differentiation and we've seen its importance. It has this key interpretation as being an instantaneous rate of change, and we see all kinds of wonderful applications involving rates of change, which is where derivatives naturally arise in many different fields or applications. So what we would like to be able to do is ideally differentiate as many functions as possible. And right now, with the tools that we have at our disposal, things like the power rule, the product rule, the quotient rule, we can differentiate many different functions. But to go any further, we really need to pause for a moment and think about how can we differentiate the trig functions. And it turns out from maybe more of a plan of attack, it's actually quite an easy thing for us. If we know the derivative of sine and cosine determine all of the other trig functions. For example, cosecant is 1 over sine, secant is 1 over cosine, tangent is sine over cosine, and cotangent is the reciprocal of tangent, cosine over sine. So if we could somehow figure out how to differentiate sine and cosine, then we can use the quotient rule to differentiate the 4 remaining trig functions. So our initial focus is going to be on sine and cosine. How can we differentiate these functions? And whenever it comes to developing a new rule of differentiation, we only have one starting point to go back to, and that would be the definition of the derivative. But before doing that, let me make just a quick note, and then we'll investigate it first from a graphical or more intuitive perspective. So the first thing I want to note is kind of more of a reminder, something we've mentioned in previous videos, is that it's important that you know the values of sine and cosine at all of the standard angles. So make sure that you know sine and cosine at those standard angles. So that would be things like, say, 0, pi over 6, pi over 4, pi over 3, pi over 2, working your way around the unit circle. And remember, if you know sine and cosine, once again, you automatically would know the values of all of the trig functions at those common angles. So on to the main topic here. How could we go about maybe getting a guess as to what we expect the derivative of sine of x? Well, one thing we previously encountered would be starting with the graph of a function and then just sketching, at least roughly, what the graph of the derivative would look like. So pictured in blue, we have the graph of the function f of x equals sine of x. And what I would like to do is just get a rough estimate of what we expect the graph of cosine to look like. And remember, our kind of approach to doing so is to first think about where will the derivative be 0. And note the derivative is 0 whenever the tangent line is horizontal. So when it comes to sketching the derivative, we know the derivative will be 0 at minus 3 pi over 2, minus pi over 2, pi over 2, and 3 pi over 2, and then so on using the periodicity of sine. Similarly, if we now kind of just pick a few key points in between, if we look at 0, if I draw the tangent line at 0, we can see, roughly speaking, that's what, a line with positive slope. And if we had to guess as to what the value of the slope would be, it looks like it goes over about as far as it goes up. So I'm going to just roughly guess the slope of that line is 1, which would mean the derivative at 0 is 1. And then if I try to make some similar predictions, if we scooch over to pi and we draw the tangent line at pi, roughly speaking, it's what, a negative slope, and looks like it could be minus 1. And then you'd find a similar thing at minus pi. And at this point, I think we probably have enough points. Let's just try to connect the dots in a nice continuous fashion and see what this looks like. So roughly speaking, it seems reasonable that it could look something like this. So this would be the graph of the derivative of sine of x. And just thinking about your experience with trig functions, do you maybe have a guess as to what you think this derivative is going to be? And hopefully you're saying it looks an awful lot like that cosine function. And I agree. Now note, this isn't 100% conclusive evidence, but it is a very compelling reason to make this guess. Note, cosine is equal to what? 1 at 0, minus 1 at minus pi and pi, and it's equal to 0 at pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, and so on. So it has all of those key characteristics you'd expect to see in the graph of cosine. So let's go ahead and move on to investigate this a bit more analytically. So in order to determine the derivative of sine, we are going to go back to that limit definition of the derivative. So let me just kind of recall for you, when it comes to using that limit definition, we think f prime x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And at the beginning of our next video, we are going to specifically focus in on applying that limit definition when the function f is sine. But in order to evaluate this limit that results, we're going to need a few other important limits. And they're the two limits indicated to the left. And I'm just going to go ahead and tell you what these values are, and note that the first one is not an easy thing for us to evaluate. If you think about substituting in x equals 0, sine of 0 is 0, 0 is 0, so it's undefined. We can't divide by 0. And in the book, they go through more of a geometric argument, and they explain why the value of this limit is 1. When we get to calculus 2, there's another limit law that can be applied, but it needs differentiation. So you'll either have to look in the book or hold off a semester to maybe see an easier approach. But for now, we'll just note that that limit is 1 and we will accept it and we will use it. Now the second limit, that is as x approaches 0 of cosine x minus 1 over x, this is something I think we can evaluate, and we can do so somewhat efficiently. In order to evaluate this limit, you might think intuitively, can I just plug in 0? And the answer is, of course, no. Not only does 0 make the bottom 0, it makes the top 0, and 0 over 0 is just an undefined quantity. But what we can do is use a familiar technique. Looking at the cosine x minus 1 in the top, what we are going to do is multiply by 1 using the conjugate over the conjugate. So this is a familiar technique in that sense, and we're going to see where it takes us. I invite you to pause the video for a moment and see if you can multiply everything out, simplify it, and see if maybe a common trig identity will help you with the numerator. So assuming you've done that, when I multiply everything out, in the bottom we would have x times cosine x plus 1. We're kind of stuck with that for the moment. And then in the top, remember when you multiply two conjugates together, you get a difference of squares. So we get the first thing squared, cosine squared x, and we subtract away the second thing squared, 1. And immediately upon seeing that cosine squared minus 1, that might remind you of a previous trig identity you've encountered, which is something that we make frequent use of throughout our calculus journey. and that would be the Pythagorean identity. Cosine squared plus sine squared is equal to 1. So we have cosine squared minus 1, which is equal to minus sine squared. So cosine squared minus 1, we can replace that quantity with minus sine squared. That is, we have the limit as x approaches 0 of minus sine squared over x times cosine x plus 1. And somehow what we want to do is get this to the point that we can evaluate the limit using either previous formulas, limit laws, properties of continuity. So one thing I can do immediately is note the negative sign is just a constant. So we can pull that in front of the limit. So this is minus a limit as x approaches 0. And then I'm going to make another observation. Something we should think about is what term in particular might be troublesome in terms of substituting in 0. And it's really the x in the bottom. And if we look up at this first limit, the limit as x approaches 0 of sine x over x, we actually have a sine x over x. So let's separate that out and see if we can use that first new limit formula. So we can write this as sine x over x times sine x over cosine x plus 1. And note, as long as the limit of each of these individual functions exist, we could break it up as a limit of the first times a limit of the second. So let's go ahead and break this up. But if we do run into any issues, we'll have to remember to kind of come back to this point. Now note, the first limit, as we mentioned, is absolutely no problem whatsoever. The value of that first limit is simply a 1. And that comes from above. The second limit is going to require just a moment to evaluate. And the question we want to ask ourselves once again is, can I simply substitute in 0? And remember, cosine of 0 is 1. So if you substitute in 0, you have 2 on the bottom, and that looks good. But what I want you to think about for a moment here, maybe pause the video and think about this. How can you justify what previous property have we encountered that allows us to simply substitute in x equals 0? And why we are allowed to substitute in x equals 0 is because of the definition of continuity. So just note, making another observation to the right here, that if f is continuous at a, then the limit as x approaches a of f of x is equal to f of a. So what we need to do is look at the function we are taking the limit of and just make the observation that it's continuous at 0. And note, this function would be continuous, well, whenever cosine x plus 1 is not 0. And the reminder is all trig functions, especially sine and cosine, are continuous within their domains, wherever they are defined, which for sine and cosine is everywhere. So this kind of combination of continuous functions is continuous as long as it's defined, which would be precisely when you are not dividing by 0. So as long as cosine is not minus 1, which means what? X is not equal to pi plus some 2n pi multiple of pi, where n is a whole number. So note, in particular, this is most definitely continuous at 0. And because we've justified it with a little bit of explanation to the right, we now just simply substitute in 0. So sine of 0 over cosine 0 plus 1. And we get back to some of these common values. Sine of 0 is 0. Cosine 0 is 1. So we have minus 1 times 0, which is simply 0. So the value of this second important limit that we are going to make use of is 0. And that's going to finish the material for this video, but remember where it is we are headed. We want to come up with a differentiation formula for sine of x, which requires us to go back to the definition of the derivative. And the only way we are going to be able to evaluate that resulting limit is by utilizing these two new formulas we've discussed. So stay tuned and take care.